Chapter 8, Section 2, Functions. This section might be one of the most important sections that you and I study. The concept of a function might just be the most important concept in all of mathematics. What is a function? Let's start with the definition. To understand what a function is, we must first understand what a relation is. A relation is a set of ordered pairs. The set of first components is called the domain of the relation. The set of second components is called the range of the relation. Look at this first example. Find the domain and range of the relation. Now this is an example of a relation, everybody. It's a set of ordered pairs. Now first of all, whenever you write a set of anything in mathematics, you use braces. This is a brace and this is a brace. So whenever you write a set of anything, you use braces. Now inside of this set are ordered pairs. This is an ordered pair, this is an ordered pair, this is an ordered pair, this is an ordered pair. This is a set of ordered pairs, therefore it's a relation. Now, the example has us considering the domain and range of the relation. By definition, the domain is a set of first components. In this ordered pair, 4 is my first component, -9 is my second component. 0 is the first component of this ordered pair, 5 is the second component, and so forth. So, let's write the domain and range. Now, because the domain is a set, right? That's what the definition says. It's a set. I will start writing my answer using set notation, right? Braces. Now, the set of first components for the domain would be 4, 0, -2, 0. So those are my entries. 4, 0, -2, and 0 again. But because 0 is already listed, I will not list it again in the set. Once 0 is in the set, it's in the set. So even if 0 appears twice or 3 times or 4 times or whatever, you only have to list it one time. In set notation, you do not repeat these elements. You do not repeat an element. All right, how about the range? The range is a set of second components. So -9, 5, 6, and 7. -9, 5, 6, and 7. That's the end of that example. Before we move on, I just want to call out something you might be thinking about. You know, when you have an ordered pair, the first component is your x coordinate when you graph, and the second component is the y coordinate when you graph. So 4, 0, -2, 0, basically these entries here, those are all of your x coordinates, and then these entries here are your y coordinates. So some people call the domain the set of your x values, while the range is a set of your y values. Now here we are at the definition of a function, okay? This might be the most important definition we write down in all of our course. A function is a set of ordered pairs. So basically, a function is a relation. Remember, a relation, the definition, I can scroll up here. A relation is simply, hold on if I can just scroll up here. There we go. A relation is a set of ordered pairs. That's all it is. A relation is a set of ordered pairs. So then when I start out my definition for a function, I have a function is a set of ordered pairs. Basically, a function is a relation. But it's a special kind of relation. There's something special happening. And here is the special thing that's happening. A function is a set of ordered pairs, it's a relation, in which to each first component there corresponds exactly one second component. Stop right there. To each first component there corresponds exactly one second component. So what that means is, here, when you look at this relation up here, this is a relation. 4 corresponds to -9. 0 corresponds to 5. -2 corresponds to 6. 0 corresponds to 7. In order for this relation to be a function, every first component, which is 4, 0, -2, and 0, must correspond to exactly one second component. In other words, once 4 corresponds to -9, 4 can no longer correspond to any other value. And it doesn't, so we're good. Negative 2 corresponds to 5. In order for this relation to be a function, 0 cannot correspond with any other value other than 5. However, when you come down the road here, 0 also corresponds to 7. Now that's a problem if you want this relation to be a function. 0 cannot correspond to 5 and to 7 at the same time, right? Not for this relation to be a function, it cannot. This is a relation, but it's not a function because 0 is corresponding to 5 and 0 is corresponding to 7 as well. Okay, so basically, once an x value corresponds to a y value, this x value here, or first component, is off the market, if you will. It cannot correspond to any other y value other than 5. So that's a problem. So this relation is not a function because 0 corresponds to more than one second component. Now, one more definition before we look at an example. Given a relation in x and y, so if you have a relation, if each value of x in the domain corresponds to exactly one value of y in the range, meaning every x goes to exactly one y, every x goes to exactly one y, then we can say y is a function of x. So basically, this phrase, y is a function of x, means every x goes to exactly one y. Every x goes to exactly one y. Then you can say y is a function of x. All right, here we go. Example 2. Determine whether the relation below defines y to be a function of x. In other words, in order for y to be a function of x, that means every x has to go to exactly one y. All right, here we go. So there is no correspondence yet defined for this relation until I draw some arrows. So I'm going to say 2 corresponds to 7. I'm going to say 2 corresponds to 8. And I'm going to say 3 corresponds to 10. This is a relation. Here are the ordered pairs. 2, 7, 2, 8, 3, 10. This is a relation. The question is, does this relation define y to be a function of x? Does every x go to exactly one y? No, you're correct. 2 is an x value, and 2 corresponds to more than one y value. 2 corresponds to 7, and 2 corresponds to 8. Because that happens, we can say y is not a function of x. So here's my justification. Y is not a function of x because 2 corresponds to 7 and 2 corresponds to 8. You can't do that, right? 2 has to make up its mind. Do you want to correspond to 7 or do you want to correspond to 8? You can't do both. Check out this next relation. I've illustrated the relation differently, but it's still a relation. Here are the ordered pairs. 5, 3, 2, 9, 7, 9. Think about this one carefully. I invite you to pause the video and think about this on your own. Does this relation define y to be a function of x? I'll give you some time to think about it. All right, I hope you had some time to think. So you should have said, yes, y is a function of x. Let me see if I can describe this for you or explain it for you. The definition for a function says every x, I'll look at this one where it says y is a function of x. Every x must go to exactly one y. It does not say that every y has to go to one x. It says every x has to go to one y. In other words, 5 goes to 3. Does 5 go anywhere else? No, so you're good. 2 goes to 9. Does 2 go anywhere else? No. 7 goes to 9. Does 7 go to anywhere else? No, 7 just goes to 9. So each one of these x values corresponds to exactly one y value. So don't get confused here. I know 9 is repeating, but that's okay because 9 is a y value. 9 is a second component. 9 is a range value. These are your range values. So it's okay for range values to repeat, but domain values, it has to be that every x goes to exactly 1y. So you don't see 2 going to 9 and then 2 going somewhere else. That's fine. 7 goes to 9. You don't see 7 going anywhere else other than 9, so you're good. All right, very good. Let's look at a couple more here. All right, check out this relation. You have the ordered pairs -3, 4, 5, 12, -3, 6. Is this a function? Is y a function of x? No. Very good. Y is not a function of x because -3 goes to 4 and -3 also goes to 6. It's a relation, but it's not a function. So I want to really be clear here. In the previous example, we saw 9 repeat. It was right here in the y column. 9 repeated itself, and then we said y is a function of x. It's all good. But in this example, -3 is repeating in the x column, and we're saying y is not a function of x. So let's be very clear. In order for a relation to be a function, the relationship between x and y is very strict on your domain values, very strict on your x values. In other words, this -3 cannot be repeating like this unless it's going to the same value, right? So that's why it messes up. Whereas the previous example, 9 was repeating, but that was okay because it was a range value. It was a y value, so it's all good there. It's the x values, it's the domain values that we're really, really looking at here, making sure every x value goes to exactly one y value. I hope that's clear. Now, moving on, a function can also be defined by an equation. Like, I don't have to draw these diagrams every time for us. I can define a function by an equation. Here I have the equation y equals 1/2 x plus 3. Let's inspect this equation and see if you and I can determine whether y is a function of x. That is to say, let's determine whether each x corresponds to exactly one y in this or for this equation. So I invite you to choose an x value at random and let's plug it in. When you plug in an x value, you may want to plug in, you can plug in whatever you want, but you may want to plug in multiples of 2. That way you end up with a whole number here and not a fraction. If you plug in any multiple of 2, 2, 4, 6, 8, 10, 12, 14, 16, 18, or even negative numbers as well, negative multiples of 2, that way the fraction goes away. If you love fractions, then disregard what I just said. But if you want to get around fractions, then plug in something, a multiple of 2. So don't plug in like 1 or 3 or 5 or whatever. I'm going to plug in x equal to 2 and figure out what y value 2 corresponds with. All right, so when I do the arithmetic, 1/2 of 2 is 1. So then I get y is 4. When x is 2, y is 4. Let's not lose that correspondence. When x is 2, y is 4. So you can see that this x value corresponds to exactly one y value. Only one. That's a good sign that this equation defines y to be a function of x. Let's plug something else in. This time I'll plug in, I don't know, -2. Okay. That would give us y is -1 plus 3. That would give us y is 2. So then the correspondence is -2, 2. So this x value corresponds to exactly one y value, that is to say 2. Now I could have you here forever, right? We can spend, eternity plugging in different x values and checking every single one. Well, that's really impossible because there's infinitely many numbers, right? But every time, I hope you trust this inspection or conclusion that every time we plug something in for x, we're going to get one thing out for y. Every time you consider one input for x, you're going to get one output for y. That is to say, every x will correspond to exactly one y value. So we can conclude that y is a function of x. So we know y is a function of x. Now, not every equation determines y to be a function of x. Just because you have an equation doesn't mean you have a function. Let me give you an example. Check this out. Determine whether each equation defines y to be a function of x. I have the absolute value of y is equal to x. This is an absolute value equation. Now let's inspect this the way we inspected the previous equation. That is to say, let's plug in an x value and see if it corresponds to exactly one y value or more than one y value. And here's our strategy. If we find that an x value corresponds to more than one y value, then we can conclude that y is not a function of x. I'll say that one more time. If you and I are able to find an x value that goes to more than one y value, the answer is no, it's not a function of x. So let's plug in an x value. What x value do you want? Remember, because x is equal to the absolute value of y, x has to be positive, because the absolute value of a number is always positive. Because the definition of the absolute value of a number is its distance from the origin. Distance cannot be negative. Distance always has to be positive. So plug in whatever you want for x as long as it's positive. So let's just plug in, 3, okay? I'm going to let x be 3. All right. Can you find a y value that makes this statement true? Well, I can. Watch this. The absolute value of, let me move the screen up a little bit for us. All right, so I can say the absolute value of 3 is equal to 3. And I can also say the absolute value of negative 3 is equal to 3. Do you see what we just did here? Remember, this is your x value right here, right? On the right side of the equation is your x value. And inside of the absolute value bars is your y value. So then these are y values. So do you see the ordered pairs here? One ordered pair is 3, 3, and the other one is 3, negative 3. There we go. Do you see this x value of 3 corresponding to more than one y value? This x value of 3 corresponds to 3 and also negative 3. So our conclusion is y is not a function of x. Just because you have an equation doesn't mean you have a function. All right, let's look at another equation. Y equals negative 6x plus 1. All right, let's check it out. Let's plug something in for x. Y is equal to negative 6. Let's plug in, the number 1 plus 1. When you do the arithmetic, you will have negative 6 plus 1, which is negative 5. So we just found that 1 corresponds to negative 5. The good news here is that this one x value here corresponds to exactly one y value. In other words, you're not going to plug in 1 here and ever get anything other than negative 5. Negative 6 times 1 plus 1 will always be negative 5. So it's looking good. Let's plug something else in for x. Let's plug in, 2. All right. So that would give us negative 12 plus 1, which is negative 11. So we found this ordered pair, this correspondence. 2 corresponds to negative 11. Now the good news here is that whenever you plug in 2 into this particular equation, negative 6 times 2 plus 1 will always be negative 11, nothing other than that. So we're finding that every time we plug in an x value, it corresponds to exactly one y value. All right, very good. Now, it's time to talk about function notation. All right, the notation y equals f of x indicates that y is a function of x. Okay, a few things here. A lot of times in mathematics, parentheses mean multiplication, okay? In this case, these parentheses here do not denote multiplication. They do not denote a group symbol either. Here, these parentheses are for function notation. So this is read as f of x. Say that with me. F of x. It's not fx, it's f of x, okay? This notation here is saying that y is interchangeable with f of x. So f of x just represents y. These two expressions mean the same exact thing. Instead of writing y, you can write f of x. And there are lots of reasons why function notation, like this on the right side, is better, more efficient than just writing y. But you can only replace y with f of x whenever y is a function of x, okay? So when you have an equation, you can replace y with f of x if it's a function. So, for example, check this out. Y equals negative 6x plus 1. We just determined that this is a function. We just determined that y is a function of x. So because y is a function of x, I can replace y with f of x is equal to negative 6x plus 1, like this. This is function notation. Now, a few things about function notation. The name of this function is f. You can name your function whatever you want. You can call it a, b, c, d, or any other letter of our alphabet, or even other alphabets, like the Greek alphabet, for example. The most common letters chosen from our alphabet to name a function are f, g, and h, but you can use whatever letters you want. The most common one that I use is f, just because that's the first letter of the word function. So f is the name of the function. And so if this is the name of the function, this value here, this expression, this number, is an input value that's coming from your domain. This is the value, the x is your input, that you are going to be plugging into your function. Now the negative 6x plus 1 is the expression that is generating the output. So this is your input, this gives you your output. Input, output, the name of your function. All right? All right, check out this example. Let f of x, this is a function, equal negative 3x minus 4, and s of t, another function, equal negative t squared minus 3t. Find each function value or output. Okay, output, another word for output is function value. When they say find a function value, they're saying find the output. Okay, so they're about to give you an input. They're going to give you something to plug in, and then you have to figure out what you get out as a result. A little vocabulary for you. This is, we're going to be talking more about this later, but this is a linear function. I know it's a linear function because this expression is linear, meaning the exponent on the x, I know you can't see it right here, but it's assumed to be 1. This is x to the first power. So that makes this linear. So this is a linear function. If you were to graph this function, it would be a line whose slope is negative 3, whose y-intercept is negative 4. I don't know if you remember, but this is mx plus b form, slope-intercept form. So this is a linear function. This one, because the variable, don't be thrown off that the variable is not x. The variable can be any letter, right? So this variable is being raised to the second power. So that means this function is called quadratic. Whenever a function is of second degree like this, we say it's quadratic. So you got a linear function and a quadratic function. All right, so here we go. The first thing they want you to find is f of 0, f of 0. Now what this means is they want you to plug in 0 as your input into function f. Don't even look at function s right now. That's not what they're asking you to do. They're asking you to go to function f and plug in 0 right there for the input. So this will look like this. The f of 0 would be equal to negative 3 times 0 minus 4. Okay, so this would give you 0 minus 4, which is negative 4. Negative 4 is the output or function value. That's it, everybody. That's all they wanted you to do. When you plug 0 into function f, you're going to get negative 4 out. Let's do it again. Now it's f of negative 3. Still go to f, ignore function s at the moment, and this time use negative 3 as your input. I invite you to pause the video and try this one out on your own. Okay, I hope you and I agree. When you plug negative 3 into function f, you get 5. 5 is called your output. It's also called your function value. All right? Now this one looks a little different. It's f of t minus 2. This one looks different only because you're not plugging in a constant. You're plugging in an expression. But it works the same exact way. You're going to go to function f, and you're going to use t minus 2, this expression, as the input right there. All right? So it'll look like this. It'll look like negative 3 times t minus 2 minus 4. Do you see what I did there? I took t minus 2 and I replaced that input variable with t minus 2. Now all you have to do is simplify. You're not solving anything, you're just simplifying. Distribute the negative 3 and you get negative 3t plus 6 minus 4. So then the output simplified is negative 3t plus 2. This is your output or your function value. All right, let's do one more. S of negative 10. You have to go to function s, finally, and use negative 10 as your input. So replace this t and that t with negative 10. I invite you to do this right now. Pause the video, replace this t and this t with negative 10, simplify, and see what you get. Now, let's check this out. Because I know students struggle with this problem, because of the signs, all of these negatives, and then your input is negative as well, I'm going to invite you to do this. Always use parentheses for your input, and also copy everything down, and wherever you see a variable, just put parentheses like this, all right? And do this in steps, right? A little bit at a time. Now, inside these parentheses, I am going to write in my input. Now, your input is not 10. Can you check your work and make sure it's not 10? It's negative 10. Now, check your work. Make sure there's a negative right here, and there's also a negative right here. I've seen so many students just put one negative. You have a negative right here that comes with the expression. It comes with the function. That's that negative there. And then you have a negative right here, which belongs to your input. All right? Be very careful. Now, be very careful here. These two negatives don't make a positive. No, they do not. Because you have to follow the order of operations, which says that you need to square negative 10 first. Okay? So that means this negative that's on the outside just gets copied down. Bring it down. Negative 10 squared means negative 10 times negative 10, which is positive 100. Negative 3 times negative 10 is positive 30. So then your final answer is negative 70. How did you do? Make sure you follow the order of operations, all right? So this example was just showing us how to find function values or outputs. All right, let's move on. All right, to wrap up this lesson, we're going to look at and study linear functions. Here's a definition. A linear function is a function that can be defined by an equation of the form f of x is equal to mx plus b. Now, this may be familiar to a lot of you. A lot of people know it as y equals mx plus b, but you and I know now that f of x means y. So this is y is equal to mx plus b, or f of x is equal to mx plus b. Your only variable is x. M and b are just numbers. They're real numbers, but your variable is x. The graph of a linear function is a straight line with slope m. So m is your slope, which describes how steep the line is, the steepness of the line. and y-intercept is 0b. So this value here, this number is giving you your y-intercept, which is the point at which it's crossing the y-axis. If you know you're dealing with a linear function, then it has to look like this. If it's a linear function, then it has to look like this. All right, guys, our last example is going to have 3 parts to it. Here's the first part. Write an equation for the linear function. Now, I want you to highlight that. It's a linear, they're telling you what kind of function you have. A linear function whose graph has slope negative 7/8. Stop right there. Slope is the letter m, right? And y-intercept 0, 14. Stop right there. 14 is your b value, right? Because remember, mx plus b, m is your slope, and b is your y-intercept. All right, so they basically gave you what m is, and they gave you what b is. Because they're telling you that this is a linear function, you know that the function has to be written like this. So let's get started. The function has to be written like this, mx plus b, because they said it's a linear function. Furthermore, they gave you what m is. It's negative 7/8 times x, that's your input, plus they told you your y-intercept is 0, 14. You're done. That's it. That is this function that they're describing. This is the linear function whose graph has slope negative 7/8 and the y-intercept is 0, 14. Now, we're not graphing this at the moment, but if you were, I would plot this point first, 0, 14, and then I would move according to my slope. Slope is rise over run. So the line would be going down. When you read the line left to right, the line would be going down because the slope is negative. All right, let's look at another example. Now, this next example, write an equation for the linear function. Now, again, highlight linear function because they're telling you that this function has to be written like this, mx plus b, whose graph passes through this point, 3, 1, with slope 9. Let's highlight slope 9, or at least write an m next to the 9. That's your m value. You know what they did not give you? They did not give you a y-intercept. Be very careful. 1 is not your y-intercept. In order for an ordered pair to be a y-intercept, the x-coordinate must be 0. So you may want to add this to your notes. That 3, 1 is not the y-intercept. I've seen a lot of people use this as their y-intercept, and that's not true. All y-intercepts have an x-coordinate of 0. So this x-coordinate is not 0, it's 3. So this is not the y-intercept. So this is what I'm going to recommend for you to do. You know the function has to be written like this. F of x is equal to mx plus b. You know that because they said it's linear. Now you also know that f of x is the same thing as y. Correct? And then what I'm going to invite you to do is identify 3 as your x-coordinate and 1 as your y-coordinate. Not y-intercept, just a y-coordinate. So they gave you an x value, they gave you a y value, and they gave you m. So let's plug in all of those numbers. So this would be 1 is equal to 9 times 3 plus b. We don't know what the y-intercept is just yet. We move this up for us. And let's solve for b. So 1 is equal to 27 plus b. When you subtract 27 from both sides, you get negative 26 is equal to b. Your y-intercept is negative 26. That was the missing piece. We needed what b was, and now we have it. So now we can write down our final answer. F of x is equal to, remember they gave us slope 9 minus 26 because your y-intercept is negative 26. All right? So this problem, notice what they gave you. They gave you, if I can scroll back up a little bit here, they gave you, take note, they gave you a point and the slope. A point and the slope. The point they gave you was not the y-intercept. In the first example, part A, they gave you a point and the slope as well, But the point they gave you in the first example, remember it was 0, 14, it was the y-intercept. This example, they gave you a point that's not the y-intercept and the slope. So I had to go about it a little bit differently. All right, let's do one more. All right, everybody, this is the last one. Write an equation for the linear function. There we go again. They're telling you what kind of function it is, which is very helpful. It's a linear function, so it has to be mx plus b, whose graph passes through -2, -11, so they gave you an x value and a corresponding y value, and is perpendicular to the graph of g of x is equal to -2x minus 15. Now, this is a very important word, perpendicular. Let me help us remember what that word implies. Okay, so add this to your notes. The slopes of perpendicular lines are opposite reciprocals. Opposite reciprocals, which means opposite in sign, and reciprocal just means flip the number over. So this is what's really important. Our line is perpendicular to this line. This line has slope -2. That means our line has slope that is the opposite reciprocal of -2. So the opposite reciprocal of -2, the opposite reciprocal of -2, that means my slope is positive. Number one, it's positive. I know it's positive because this guy's slope is negative. That means mine is positive. Furthermore, this guy's slope is -2. You can view that as -2 over 1. That means my slope is going to be 1 over 2. If he is 2 over 1, then I'm 1 over 2. So my slope is positive 1/2. Did you all get that? There is an invisible, if you like, here. Watch this. I'm right over here, right? That -2 there. If you want, you can write that as -2 over 1. So what you need to do is not only take the opposite in sign, right? Opposite in sign. So he's negative, that means I'm positive. But instead of 2 over 1, you got to flip it over and it becomes 1 over 2. This is our slope. Now, I don't know if you want to, at this time, write this in your notes as well, or maybe I can write it down later. But the slopes of parallel lines, if this problem had said parallel, the slopes of parallel lines are exactly the same. You may want to add that to your notes right now. The slopes of parallel lines are exactly the same. They are equal. But the slopes of perpendicular lines are opposite reciprocals. All right, you guys, I'm going to proceed with this question now. All right, so here we go. F of x is equal to mx plus b. I know that our function must look like this because they told me it's linear. I'm going to plug in everything I know, which is, I'm going to plug in -2 for x, I'm going to plug in -11 for y, and I'm going to replace m with 1/2. Okay? Before I do that, though, let me move up all the way here. I am going to, f of x represents y, right, everybody? There we go. All right, so y is -11. Your slope is 1/2. X is -2, and we don't know what the y-intercept is yet. Cool? So then this is -11 is equal to -1 plus b. When you add 1 to the left side, you get -10 is equal to b. So b is -10. All right, everybody. That's the last piece we needed in order to write down our final answer. Let me scroll this up here. So then our final answer looks like this. F of x is equal to mx plus b, right? So our final answer is f of x is equal to, our slope is 1/2, times x, which is your input, minus 10. -10 is your y-intercept. We had to find that. All right? I hope this made sense for you. I hope this was, maybe some of this information, I'm not sure. Maybe some of this information was good just review, while other parts were, oh, that was brand new. Maybe all of this is brand new. I'm not sure. At the end of the day, I hope it was informative and you learned something. All right? All right, good job, you guys. I'll catch you in the next lesson, which will be 8.3, entitled Graphs of Functions. All right, see you later.